For a chemical equation to be valid, there must be the same number of each type of atom on both sides of your reaction arrow. It's often going to be your job to make that count even, which takes some practice. I'm going to demonstrate balancing equations with 3 examples in this video. These examples have been chosen because there's a different time-saving trick to look out for in each of them. But even with these tricks, these 3 equations could be balanced using whatever systematic approach that you choose. All of these approaches, and there are a lot of them, should involve some pretty similar steps. First, make sure that you review your equation and you ensure that you've rewritten it correctly. This seems like a silly thing to point out, but if you don't transcribe it correctly, you have no chance of balancing it correctly. Then, determine the atom count that you have right now. Take both your subscripts in the formula itself and the coefficients in front of that formula, if those are present, into account. If you're lucky, there will be the same number of each type of atom on both sides of the reaction arrow right now, and you'll be all done. It's not a super great quiz question if that's the case, though, so you'll likely have to add some coefficients to your equation. Changing a coefficient in front of a formula changes the number of formula units you have, while changing the subscripts in a formula changes the entire compound that you have. You'll need to take care to do the former and not the latter. Lastly, double check your atom count now that you have your coefficients in place. If the count still isn't equal on both sides of the reaction arrow, then you're not done yet. Let's get going with the reaction of sulfur dioxide and oxygen, which forms a single product, sulfur trioxide. For the benefit of those mostly new to balancing reactions, I'm going to add some visual representations of each of our molecules for this example. Sulfur is the lighter, slightly larger circle, and oxygen is the darker, slightly smaller circle. So that no one tries to take my chemist card, I need you to know that these colors are completely arbitrary and have zero to do with the appearance of either of these elements. Also, the atoms in each molecule are kind of where they would be after bonding, but know that I'm working towards visualizing an atom count more than a molecular shape here. So these are definitely not drawn to scale, they're not drawn with the correct bond distances, and they're not drawn with correct bond angles. That said, let's review our current atom count. When counting atoms, you'll want to review each element separately and then to count all of the atoms of an element together, regardless of how many places it shows up on that side of the reaction. For example, you'll just clump the 2 oxygen atoms from the sulfur dioxide in the same count as the 2 oxygen atoms from the molecular oxygen, giving you 4 total oxygen atoms on the reactant side. If you had more than one product, you'd use the same reasoning on the product side as well. But since we only have one product, we can get our entire atom count from our single molecule of sulfur trioxide. There are the same number of sulfur atoms on each side of my reaction arrow right now, but this isn't the case for the oxygen atoms. And since there are more oxygen atoms on the reactant than the product side, our equation isn't balanced, and we have to work to fix that. Notice that there are an even amount of oxygen atoms on the reactant side, and there are an odd amount of oxygen atoms on the product side. The easiest way to start balancing in a case like this would be to double the number on the odd side. So place a 2 in front of sulfur trioxide in your balanced equation. This gives me an even number of oxygen atoms on both sides, and even though my atom count's still not equal, and I managed to goof up the previously balanced sulfur atoms, it will ultimately be easier to get to that point if this is the first step that I take. Now at this point, make sure that you understand the atom count on the product side. The subscript of 3 in the formula on that oxygen tells you that there are 3 oxygen atoms per every molecule. The coefficient of 2 tells you that you have 2 of those molecules. So when you determine an atom count, you'll need to consider both of those values, as their product gives you the actual count for that element. Balancing one atom will often unbalance others. Yay! And getting the whole equation balanced correctly sometimes involves a lot of back and forth. This example is no exception, as we are both closer and further away from done than we were before. In general, if there isn't a trick I want to follow, I just balanced equations from the left to the right, which means that I would shift back to the reactant side of the equation right now to see what I would need to adjust. We need twice as many sulfur atoms as we currently have on that reactant side. We only have one in place. So the sulfur dioxide molecule is it. That's the only place that we can adjust sulfur. Our next step is to simply add a coefficient of 2 in front of that sulfur dioxide. It's a good idea to count atoms after each addition of a new coefficient, especially when you're beginning to practice balancing equations. Now I have 2 sulfur atoms, 4 oxygen atoms from the 2 molecules of sulfur dioxide, and 2 additional atoms of oxygen from the single mole molecular oxygen. The number of each type of atom is equal on both sides of my reaction arrow now, so I'm done balancing. Remember that if we only need one of a compound, as is the case with the oxygen here, we will not include the actual number 1 in front of that compound. It's just implied. I'll move through these next two just a touch quicker and without the visual representation. If that helped you, I encourage you to keep doing it though. Grab some different colored pens or highlighters to help you keep track of what is what, or use different shapes, such as squares, triangles, circles, and X's, if you happen to be a PlayStation person. As promised, this one also has a trick to make balancing a touch easier. Notice that barium hydroxide includes a polyatomic ion, the OH group. Since polyatomic ions are collections of covalently bonded atoms that carry a shared charge, they will move from one cation to another in equations like this one as a unit. Meaning, if you start with a polyatomic ion, you'll end with that same polyatomic ion. We'll predict the products of equations like this guy, but for now, know that it's in your best interest to treat these polyatomic ions as a unit and balance the unit across the reaction arrow versus balancing the pieces of that unit. I have hydroxide here, but this would be a similar story if you had acetate, phosphate, sulfate, ammonium, etc. You might be concerned that you don't see a hydroxide ion on the product side right now. Fear not, because a water molecule is really just a hydroxide ion interacting with a hydrogen ion. It helps a lot of students to avoid thinking about water as H2O, and rather to think about it as HOH. This makes it easier to visualize the hydroxide group. It will also help visualize what's actually happening when you get to acid-base chemistry in 117. Since this one is slightly more complicated than the last, it might be a good one for a table, if that's your method of balancing, which is kind of what we did on the last one, only in a different format. So here's my table. R stands for reactants and P for products. Could I have written those words out? Yes, but is this closer to what you'll probably scribble on your scratch paper come quiz time? Also yes. So here we are. I've included a row for each piece that I have to balance. I've included the hydroxide ion as one piece, and I'll count both that single oxygen and single hydrogen atom that are involved in that hydroxide at the same time as a unit. I have to also list hydrogen on its own line as well, because it happens to also be present in this reaction as part of hydrogen bromide, making it a standalone element that isn't part of that polyatomic ion. Count the number of each species on each side of the reaction arrow and fill in your table. Be careful because it's fairly easy to jumble values from one side to the other because things show up in a different order. Always double check atom counts before you start balancing. As you can see, there's a few places where your atom counts don't match, so let's get to work. Because it's what I tend to do, let's start all the way to the left with the reactant barium. This table shows me that there's 1 on each side of my reaction arrow, so the barium appears balanced for the time being, and I'm going to leave it alone for now. Moving towards the right, I run into the hydroxide ion next. There are 2 involved with that barium hydroxide salt on the reactant side, but only 1 involved with the water on the product side. Adding a coefficient of 2 to my equation in front of the water should balance that polyatomic ion. It also changes the number of hydrogen ions present, and I'll need to update both entries in my table to properly keep track. You can think about your next move one of 2 ways. They're actually the same move in this case, but lots of times they won't be. You could A, balance what you just unbalanced, which would be the hydrogen. Or you could B, move back to the reactant side and move on to whatever is next as you're moving towards the right. Since we took care of barium and hydroxide, hydrogen is the next thing we run into moving from the left. Our table shows us that we have half as many hydrogens as we need on the reactant side. So again, if I add a coefficient of 2, this time in front of the hydrogen bromide, I should be good. But again, count your atoms that you affected by this addition. It looks like we're done, but we should always double check our balanced equation. It won't take very long, and it could mean the difference between a right and wrong answer come quiz time. Remember to take both subscripts and coefficients into account when you're counting your atoms. There's a single barium cation on the reactant side and a single barium cation on the product side, so barium's balanced. There's 2 hydroxide ions in the barium hydroxide salt and a single hydroxide in each of the 2 water molecules, so the hydroxide ions are balanced. There's a single hydrogen atom in each of the 2 hydrogen bromide molecules on the reactant side and a single hydrogen ion in each of the 2 water molecules on the product side. So the hydrogen atoms are also balanced. Lastly, there's a single bromine atom in each of the 2 hydrogen bromide molecules on the reactant side and 2 bromides in the single formula unit of barium bromide on the product side. The bromine atoms, therefore, are also balanced. This is an example of a double displacement reaction, and you'll work with a lot of double displacement reactions by the end of this term. It's a great idea to practice as many of these as you can find. There's going to be a lot of them in section 2.2. This reaction is an example of a combustion reaction. I know this for a couple of reasons. First, we have an organic compound, which is the C8H18O2. When you see this combination of elements, think organic substance. Another clue this is a combustion reaction is the presence of O2 as a reactant. O2 being present as a reactant won't always result in combustion, but combustion reactions involve burning, and you cannot burn anything without oxygen present. The last and probably the best indicator that this is a combustion reaction are the products that are formed. Burning organic compounds that contain only some combination of CH and O in the presence of oxygen will always yield carbon dioxide and water. Since all 3 of these things are true, we definitely have a combustion reaction here. You might be wondering why I think that's important, especially if you previewed the rest of the module and you realize that combustion isn't even on our list of reaction types that I want you to be able to work with. You will want to recognize these, though, as balancing the atoms in a certain order makes these much easier to deal with, and you will see a lot of combustion reactions as you are practicing balancing. Carbon will be part of the organic compound on the reactant side and carbon dioxide on the product side. And for our purpose, that's going to be it. So we'll start these all the time by balancing the carbon first. We do that by changing the number of moles of carbon dioxide present in our formula. Once we have carbon tackled, we'll balance the hydrogen atoms by adding a coefficient for water. After that, you'll just be left with oxygen atoms, which will definitely be in 2 places on the product side and could be in 2 places on the reactant side, which is why it's always saved for last. You want to add a coefficient to the molecular oxygen to balance all of the oxygen atoms. Now, a few notes before we move on to the actual example. This particular organic molecule includes carbon, hydrogen, and oxygen, but you will also see a lot of organic compounds that only include carbon and hydrogen. You'll balance the elements in the same order for those organic compounds as I am this one, only you'll only have oxygen in one place on the reactant side, making those a touch easier. Know that combustion reactions can end up with some crazy large coefficients. Because of this, the chemists will often include fractional coefficients for oxygen if they're actually reporting this anywhere. Don't worry about doing that for me. I'll expect all coefficients to be reported in the smallest whole number ratio. And lastly, sometimes you'll notice that you can't balance the oxygens with whole numbers because of the coefficient for the water molecule ends up being odd, giving you an odd amount of oxygens. It's easiest to double everything you've done up to that point to finish it out. Now that probably doesn't make sense, but no worries, because we'll need to actually take that step in this example. All right, we know we've got to work on carbon first, so let's do that. There are 8 carbon on the reactant side, so I need to work towards 8 on the product side. If I had 8 carbon dioxide molecules, that would do the trick. So add a coefficient of 8 in front of the carbon dioxide. Second on our list was hydrogen. There are 18 of them in my organic molecule on the reactant side, so I have to work towards getting 18 on the product side. Now, this is where we run into issues, as in balancing the hydrogens by adding this 9 in front of the water results in an odd number of oxygen atoms on this product side, which means I won't be able to balance this with whole number coefficients without doing something because I only have even numbers of oxygens on the reactant side. So the easiest thing to do at this point, if you get to this point, and this is the case, is to double all of the coefficients that you've already put in place, including that implied 1 in front of the hydrocarbon. Doing so will give me an even number of oxygen atoms on both sides. Have some faith right now and follow along if you currently happen to be irritated with me. Now is a pretty great time for an atom count since crazy things seem to be happening. We've definitely tackled the carbon and the hydrogen, but we're still way off on the number of oxygen atoms. Notice that here I've separated where they came from in my count. I have 4 from the organic molecule and another 2 from the elemental oxygen. Now I'm not going to mess with those first 4 because if I do, I goof the carbon and the hydrogen and I don't want to do that. So I'm going to have to add a coefficient in front of the molecular oxygen that can make up the difference between the 4 and the 50. So here's how we're going to play this. I know that I need a total of 50 oxygen atoms on the reactant side because that is what I have on the product side. I also know that there happen to be 4 oxygen atoms that I refuse to mess with. 2 atoms each from the 2 molecules of my organic compound. Consider these fixed, meaning unchangeable. Now that leaves me with a deficit of 46 oxygen atoms on my reactant side. Since I've decided that I can really only change the coefficient on the O2 to get me to that 46, that means I will need a coefficient of 23 in front of the molecular oxygen. Because I started with 4 atoms on the reactant side, and I am adding another 23 times 2 or 46, all of that gets me to 50. Not all combustion reactions will involve the doubling of the coefficients like this one did. Lots of students prefer to actually begin combustion reactions by doubling that hydrocarbon in the first place. This approach is more than fine. Just know that you'll usually have to have all your coefficients at the end of the process. Always report the lowest whole number coefficients when you report your final answers.